So I'm going to start you off with the very beginning. How do we get plate tectonics? Okay. So this doesn't have the word plate tectonics in it anywhere, what we're seeing right now. So, oh, and by the way, these questions, just as not just an aside, but as an important piece of information, last time we talked about, actually the last couple of times, we've talked about this place on your Blackboard website. There's a folder for reviews, and there's a folder for weekly reviews. And those weekly reviews have open-ended questions in them. And so I've mentioned them to you. I've shown them to you and said, hey, these are ways to help you keep track with your reading, with your note-taking, with your studying. You probably, as you see some of these questions that pop up on the screen, you're like, oh, if you've been looking at those weekly review questions, here are some of those weekly review questions. So these are the big concepts, some of the big concepts that we are covering, right? So those are the things we want to know, we want to really focus on. So make sure you're using those. Take advantage of those questions because they will help you focus on what you need to do here. All right. Continental drift is what we see here. Continental drift. So we see a new term, continental drift. We see a new name here, and that name is Wegener. Now, Wegener is a last name. That W does have a V sound to it, and that's because Alfred Wegener, this guy's name, Alfred Wegener, he's German, or he was German, and so Alfred Wegener, right? Alfred Wegener comes up with this concept called continental drift. This is the seed for plate tectonics. So this is the very beginning. This is the seed for plate tectonics. So let's understand what continental drift is. Now I'm going to take you to plate tectonics first so we can just be reminded of where we are today. So remember that plate tectonic theory, we touched on it briefly last week. Plate tectonic theory, this idea that the Earth is divided into lithospheric plates. Now, you all tell me, the lithosphere, how thick is the lithosphere? What is the thickness of the lithosphere? So we learn that with our layers. Thickness of the lithosphere, everybody should know that one. Yeah, there we go. Thank you all. Claire, Mohammed, Haley. Yeah. So 100 to 150 kilometers, right? So the lithosphere, 100 to 150 kilometers thick, it is composed of the crust and the upper mantle. Okay. So what we're looking at here is we're looking at the plates of the Earth, which are lithosphere, and it's really like the lithosphere is cracked on the surface of the Earth. And so the black lines we're seeing are like the cracks on the surface of the Earth, which divide up the lithosphere. It is not quite as simple as thinking of it just as being cracked because this is dynamic. These plates move, they move relative to one another, they change shape, they change in number, but we'll kind of get to all of that. But this is where we are now. Plate tectonics. Notice this, strange map of the Earth where we see continents and oceans together on one plate. And so, for instance, we look here, and this is the North American plate. I'll just abbreviate. We can see it written up here, North American plate. And it includes the continent of North America, but it also includes a lot of ocean as well. All right, that'll become important to us later. How do we get to plate tectonics? And then we'll start talking about what plate tectonics means, what that helps us with. But how do we get there? Let's go to Alfred Wegener. Let's go back to him. Alfred Wegener is doing his work in the early 1900s, think 19 teens. This is a little over 100 years ago, 19 teens. Alfred Wegener is a meteorologist. So he is really interested in climate, and he is very interested in past climate. And that gets him studying a lot of interesting things, including geology. So he begins to look at the continents, the continental land masses. He's looking at changes that have happened on the continental land masses. And he starts to see, he looks at fossils. Fossils are related. What kind of life was in existence at different times throughout the past? That's related to past climate. He starts to put together an idea. a hypothesis. So Wegener puts together the hypothesis of continental drift. Now, what does continental drift mean? You can kind of see it represented over here on the right-hand side, though you might not know what you're seeing until you look down at the bottom. So Pangea, you have heard Pangea, right? Can nod. Pangea, that term Pangea. Yeah. So Pangea, and you can write it a little more simply. AEA is fine, or PANGEA is fine as well. So Pangea. So Pangea was the supercontinent. So we know of that one, or it was one of. We've had several supercontinents, couple of supercontinents. But Pangea, all the lands together. This literally means all lands, by the way. So Wegener comes up with this term. He coins this term. He creates the term Pangea. If you've heard the term Pangea, it is because Wegener, he originated it. So Pangea, pan meaning all, Gea meaning lands. This is all lands, literally all lands that we're seeing here. So Pangea. Wegener says there was a supercontinent Pangea and it began to split apart. The continents drifted apart. These are his terms, his words, drifted apart to their present day locations. Okay, so Pangea, continents drifted apart to their present day locations, continental drift. All right, so what is his evidence for continental drift? Because I said he starts to put this together. He has some research that he's done. He's made some observations. He does some research. He poses this hypothesis, and then he does a little bit more research because he wants to figure out, okay, what really supports this hypothesis? What do I see that supports it? Now, the first thing, and this one's pretty straightforward, continental drift. If we look at the location of the continents today, we can see that they look like they fit together. I mean, you've probably looked at some point in time in the past at South America and Africa and thought, gosh, they look like they fit together. Now, this is a really simple piece of evidence. So we are enumerating, by the way, we're enumerating pieces of evidence that Wegener has to support his hypothesis of continental drift, okay? So we're going to have 4 of these. We're just going to have 4. There are more than that, but we're just going to list out 4. 4 pieces of evidence that Wegener has to support continental drift. So one is this puzzle fit of the continents. Jigsaw puzzle like fit. And it's not just South America, Africa, it is also east coast of North America. I mean, look how this, if you squeeze this together, you're like, yeah, that really looks like it fits together. A reminder again, need to be able to see your faces, Geo, Stephen, need to be able to see your faces on there. So please just, yeah, instead of sitting up, point your camera down, we can see you, and that way we can see your faces. Yeah, there we go. Stephen, if you point your camera down, that way we can see you instead of, because I know if you're taking notes, if you're leaning over, this way we can make sure that you're still there, not just the top of your head. So this is the puzzle fit, 1. 2, so there's Pangea, right? 2, and this is much better evidence, is fossil evidence. Now, you're writing notes, you're going to write puzzle fit, that one kind of, okay, I know what that one means. You're going to write fossil evidence, and then, all right, let's explain that a little bit. Don't just write fossil evidence in your notes. Let's write what that is so that you remember it later on. So we're going to use a couple of examples, but let me give you the overview first. This is showing continents together, and this is really southern hemisphere continents that it's showing kind of together in Pangea. These continents show fossils of organisms that are the same. The same organism exists on multiple continents. And these are just 4 examples they've got up here. We're going to point out 2, and there are a lot more than this. There are a whole host of fossils that we see the same organism on multiple continents, if not all of the continents that were in existence with Pangea. Now, the key to this is that all of these organisms are older. So all these fossils are older than about 200 million years. So they all existed 200 million years ago and more. these organisms. All right, so there's a certain range of time there that we see this. And why 200 million years? Now, Wegener didn't have that time. We didn't have that timeline. We didn't have the dates on this then. But 200 million, that's when Pangea started to break up. So we know that now. So these fossils we see, let me point out two. We're going to look at this one right here, Lystrosaurus. So this one right here. Lystrosaurus, about the, I don't know, medium to large size dog. You know, that's what Lystrosaurus, kind of how big Lystrosaurus is. Does Lystrosaurus look like a good swimmer to you? You can just nod your head or shake your head. Lystrosaurus does not look like a good swimmer. And so Lystrosaurus was not swimming across ocean basins to get from continent to continent. And we do see that Lystrosaurus exists like on Africa, and this isn't just one fossil, this is hosts of fossils, right? So communities of fossils. Lystrosaurus exists on Africa, India. Now, you know, okay, those are connected by land today, but Antarctica. One, Antarctica doesn't have a climate that would allow Lystrosaurus to exist today. But two, how did Lystrosaurus get from one of those continents to the other one of those continents? Lystrosaurus was not swimming. Wegener says, hey, very simply, it's because the continents were together. Lystrosaurus didn't have to swim. These continents were all together. Same for, and this is the other one I'm going to point out here, is same for this one, which is Glossopteris. So here's the other one for you to know, Glossopteris. And this is a plant. So this is why I use this one. This is a little different. This is a plant, kind of fern-like plant. Let me show you. There's a picture, right? So this is a fossil of Glossopteris, we can see. But Glossopteris has big seeds. You can see that in the fossils. And Glossopteris exists on really all of these continents. Now, how does a plant get from one continent to another across an ocean basin? Today, this is pretty easy. Today, we transport stuff. We have so many different invasive species out there in South Central Kentucky because people transport things. Birds transport seeds. Now, birds don't tend to transport seeds incredibly long distances, so even today, but birds didn't exist 200 million years ago. So that's an interesting point to think about. So they weren't doing transportation. So it wasn't, this was not blowing in the wind, you know, across these ocean basins. The seeds were too large. They weren't floating. The seeds are too large. This is because the continents were together. And so Wegener pieces that together. He's like, you know, how else? And like I said, these are not the only ones. If you're skeptical of these, you can look. There are lots more. So Wegener puts this together and he says, hey, there's a really simple explanation behind why these organisms all exist on all of these continents. And it's because they weren't separated by ocean basins then, they were together. Simplest explanation, right? So there was two. Okay, so we've got the puzzle fit of the continents, we've got the fossil evidence, and moving into the third piece that Wegener has, I told you he was really interested in paleoclimate. Paleo, when we put paleo in front of something, we just mean past, right? So I kind of ran out of room there for my E, but paleoclimate. So past climate he's looking at. And if we think about past climate, just here in South Central Kentucky, how many of you have picked up fossils in South Central Kentucky? Yes. Hey, so any of you who've picked up fossils, what do the fossils look like? What kind of fossils have you picked up?
Mainly plant life,
Okay,
like coral and stuff, crab.
Okay, so corals are they're animals. We might think about them as being, you know, because they're stationary. We think about them being, but they're like little animals. Crinoids, I see. Colton, thank you. So yeah, these are little animals as well. Interestingly, even though they're attached to the bottom of the seafloor. So we do have some plant life that we see from time to time. We see a lot of ocean life. So things that existed in a warm, shallow sea environment. Oh, some fossilized wood. Interesting. So that fossilized wood may have been transported here from somewhere else. You may have been lucky to find that there. We don't see a lot of that yeah, we don't see a lot of that here in Kentucky. So we do find, though, a lot of coral, a lot of shells, a lot of ancient shells. These things, 300 million years ago or so, we were a warm, shallow sea environment. We were much more like the Bahamas at that point in time. So today, we wouldn't be able to support corals growing in Bowling Green. That just wouldn't happen. But 300 million years ago, absolutely, coral was growing in Bowling Green and the land that becomes Bowling Green. And we can see a little bit of that from what's going on in this image. And so notice where we are. So if we think about, like, approximately where Kentucky is, I don't know, just, maybe around where the top of this palm tree is. So in this, because obviously North America looks different here, notice how close we are to the equator in the past. We were actually a little south of the equator at one point in time. So we are not there now. We are not tropical now, but we were a tropical environment. One of our paleoclimates was tropical. So we were not just a warm, shallow sea, we were a tropical shallow sea. So Wegener is looking at these past climates, and he sees that there is a connection in these past climates across continents. Now we can see that a little bit here, these that would have been together. We can kind of see these tropical climates together in places that we don't expect that, even in places like Europe and the south part of Greenland, right? But he also, now he was very interested, he did a lot of research in Greenland. He was mostly interested in glaciers. And so look at all the glacial activity down here in South America, South Africa. Notice how a big part of Africa is covered in glacier. India, Australia, Antarctica. Antarctica is covered in glacier today, but this is continental glaciation, like covered up with glacier, not right at the top of a mountain. I'm talking about covered up with glacier. And so if we consider why that is and what Wegener was talking about, one, he was saying the continents were shifted into different locations on the planet. We were closer to the equator. Africa was closer to the South Pole, and so it was colder, right? He also looks at, and we're not going to get into the details of this, but he also looks at the direction of the movement of those glaciers. And so he can connect that out in these continents. So Wegener says, okay, paleoclimate, and there's a lot of detail with that. Paleoclimate allows us to understand that these continents were once connected. And yes, the question about sharks and finding shark teeth in Mammoth Cave. Yeah, we were a sea. And that has to do with isostasy, concept we dealt with previously, and how our land, the continental landmass, was a little bit lower in the past. So isostatic, sinking a little bit, and the sea was able to have inundated this portion of North America. And so, yeah, we were able to have sharks in this area. And absolutely, Claire, yeah, Falls of the Ohio. If you haven't been to the Falls of the Ohio, especially at a low water time, where you can really walk out there and see it, that's an excellent example to see ocean fossils, to see how we were this warm, shallow sea. Thanks for that. All right. We got one more piece of evidence for Wegener that we're going to get into, okay? And this is really a combo one. So this is really a couple different ones, but we're going to do a combo with it. So this is, notice here's South America and Africa together, as Wegener would have envisioned them in Pangaea. And so notice what it's showing us. Now, you may not know some of these terms, and that's okay. This is age. This is dealing with age, Archean. This is just a time in Earth's past. And so this is rocks of the same age. And so we would see rocks of the same age match up across the continents. We would also see rock structures. And so this is talking, again, this is a time in Earth's past, rock structures like ancient mountains matching up across these continental landmasses. So how are we going to list this out as the fourth piece of evidence? Rock type and rock structure. Rock type and rock structure match across these continents that were once connected. If we reconnect them, right? If we reconnected them, we would see that these puzzle pieces don't just match up with shape, they also match up with substance. What is on them? What is the rock type, and rock structure? And that includes age, but rock type and rock structure. Let me give you another example of this, not just South America, Africa, but one that's a little closer to home, and that's the Appalachians. The Appalachian Mountains were formed when Pangea formed. So this was a collision, a continental collision that occurred, and the Appalachian Mountains formed as a result of that. Now, the Appalachians, as a mountain chain when they originally formed, would have extended all the way through this entire area that you're looking at here. So here's the ancient Appalachian mountain range all through here when these were together. You're seeing ocean basin in between them now, but when these were together. As Pangea split up, it split off different parts of this mountain chain, this rock structure, into different locations. And so we can see Greenland has part of the Appalachians in it. Isn't that interesting? It's the same mountain range. It was created at the same time during the same processes. Europe and Great Britain, they have some of the same parts of the Appalachian Mountains. It's really interesting to think about that way. Africa has some of the Appalachian Mountains. Like, we don't think about it that way, but that's really what it is. And so Wegener's putting these things back together. And he said, okay, this is why that is. This is why those structures are there. They were once together. So there's number 4, questions about Wegener's evidence. Okay. Now, sadly for Wegener, Wegener comes out with this. Now, he comes out with this about 1917. He prints this book, The Origin of the Continents of the Oceans. 1917, something else happening in the world. And some of you are like, yeah, that's World War I. And so not many people are paying a lot of attention to this German book about this. He goes through several different iterations. Finally, kind of in the 20s, he starts to get read more worldwide, and people start to ask questions. And so he, is being asked questions by the scientific community, because that's the way this works. And one of the questions that they ask him is an important one. And that is, okay, Wegener, we see your evidence, and there was a lot more than this. We see your evidence, and this is interesting, but how do the continents move? How do the continents move? Hey, Wegener, how do the continents move? And Wegener does not, well, he does have an answer for this. Let me give you his answer. Okay. So Wegener's answer is, and this is what he put in his book, Wegener says, it is because of the spinning forces of the earth, the centripetal forces of the earth, and that causes the continents to plow through the ocean basins. Now, that's kind of his terms, right? So the spinning of the earth causes the continents to be able to plow through the ocean basins. Now, there's a problem with that. And even you sitting there listening to that, you're like, that sounds weird. And in the 1920s, scientists weren't just like, that sounds weird. They actually said, the math doesn't work on that, right? The physics doesn't work on that, Wegener. There's no way that those forces are great enough to cause that rock to change in that way. Continents aren't plowing through ocean basins in that way. That is not a strong enough force to make that happen. And so if we know anything about a hypothesis needs to be supported by every piece of evidence that you have. And so if this was his evidence that the continents were moving, now his hypothesis has failed, right? This did not support his hypothesis at this point in time. And so geologists said, nope, go back to the drawing board. Unfortunately for Wegener, Wegener died in the 1930s. So he didn't really get to go back to the drawing board to figure out a lot of these things. And I will say, he didn't have some of the science that we have now to fall back on as here's really what's happening. So here's really what's happening. How do we get from Wegener with a hypothesis that has now not been supported? How do we get from that to today talking about Wegener? One, two, talking about plate tectonics, which the seed of plate tectonics was continental drift. How do we get from one to the next? And how we get from one to the next has to do with the development of more science. And I see the question, so erosional patterns. So it's really, Andrew, it's the continental shelf areas of the continents that match. And so we even go like underneath the ocean. So it's not just the continental landmass that's above sea level, go down to the level of the continental shelf, and the match is much better there. And so we can see the match really well there. So I hope that helps a little. Okay. So how do we get from one to the next? How do we get from one to the next? All right. Before we go there, let me pull up a poll for you. Hey, it's a poll. Here's the poll. Now, this is don't submit until you choose everything. So notice, so if you have to expand that window out, you can expand that window out a little bit to see all the responses. There are 1, 2, 3, 4, 5, 6 down there at the bottom that you need to read. So make sure you can see 6 of those. So the question about, hey, which of the following were pieces of evidence that Wegener cited in support of continental drift? So this is Wegener. What was his support of continental drift? And you get, with the others, you get a little preview of some things we're going to talk about. What did Wegener select? All that apply. So this is basically you are going through and picking the 4 that we just talked about. So again, we usually take about a minute for polls. So maybe about another 15 seconds on this poll. We've got 4 people still need to participate. 3, 2, 1. Closing out in 5, 4. Oh, there's everybody. Okay, so I'm going to end poll, and I will share the results with you. So here's our results from the poll. The good news is most everybody selected the ones that were there, that were Wegener's evidence, right? So the 4. And so we can see the ones that have the most answers, those are the 4. We just went through a puzzle fit of the continents, the fossils that are widely distributed, the paleoclimate evidence, the matching rock types and structures. We did have a couple of folks who added in some others that we did not talk about. We did not talk about associated with Wegener. And we had a couple of folks who did not choose all 4 of those. Maybe you just submitted early and didn't see all of those. But one of the things I would say when we do these polls, this is a good way to check yourself. Have I been taking notes? Have I been paying attention in class? Have I been present in class? Because these are 4 things we just went through. So hopefully should have been right there in everybody's mind and right there in your notes. So these are kind of good checkpoints for as we go through some of these things. Any questions about that? Okay. All right, so I will stop share with the poll there. All right, so let's get back to new evidence. New evidence. Okay. So this has some terms for us. This has some things that maybe we don't know. Magnetic declination, inclination, we're going to go through these. And then something called paleolatitude. Now, we might already have a sense what that is because I said paleo is just past. And so if we say paleolatitude, past latitude. For instance, we talked about the past latitude of South Central Kentucky because we said, hey, we used to be closer to the equator. So our latitude, right, those horizontal lines that run around the Earth, like the equator. So latitude, our latitude in the past was different, right? So that's paleo latitude, thinking about that. Now, declination and inclination are a whole different thing. Now, let me explain first, and then we'll get into declination and inclination. Let me explain first a little bit about Earth's magnetism. So Earth has a magnetic field. I think we all know that. Earth has this really great magnetic field that helps protect us from solar radiation and such. Earth's magnetic field acts a bit like a dipole magnet. Now, let me show you that. So Earth acts, I'm going to come back to that image we just had, but Earth acts a bit like a dipole magnet. So let me share with you a dipole magnet example for us all to see. So let me get that full screen and then I'm going to share that with you all. Okay, there's no audio with this or no audio that matters. So don't worry about the audio. But what you're seeing here is this person has in a little jar with a tube running down the middle. They have a bunch of iron filings. So it's just shavings of iron that are there. And they're obviously going to react to a magnet and be attracted to a magnet. And what they're going to do is they're going to put this metal magnet, you can kind of see it poking out down here at the bottom. They're going to put this magnet inside that tube. This magnet we see there is a dipole magnet. Now, what I mean by dipole, it has two poles. This would be like a north end and a south end. If you've ever played with magnets, a black end and a red end, right? So if you've ever played with magnets, those opposite ends, it's a dipole magnet. It has a different charge on either end. Okay, so let's watch what happens as they do this. And Gina, we need to be able to see your face on your video. You see what happened? I'm going to back that up because it's pretty cool. So they put the magnet in and notice what happens to these iron filings. So they flip it over so the iron filings all get attracted. Okay, so to pause there. So what you see, notice there are some loops. You see how there's some loops within this? So some of the iron filings actually form a big loop from one end to the other. We see that some of the iron filings on the end are almost sticking straight out at the very end. If we could get to the very end of this, we can't in this situation because the way that empty space runs down through the middle, they would be sticking straight up on the end. These are sticking more straight out. As we get closer to the center, do you see they lie down flat? Right? Okay. This is how this shows us the magnetic field of the dipole magnet. So this shows us the orientation of the magnetic field of a dipole magnet. Now, let me go back and we're going to talk about what that means. Okay, so going back to our slide that we had previously, the magnetic field of the Earth here is represented by these white lines. So all of these white lines are representing the magnetic field of the Earth. What we just saw is those iron filings representing that, showing that magnetic field in a very visual way. So you could see the loops like we see here. You could see that closer to the center. So here's our dipole magnet. Now, we don't really have a dipole magnet at the center, right? I'm just using this as an example because this is how our magnetism works. We have a north magnetic pole and we have a south magnetic pole. And so our magnetism functions like a dipole magnet. It's not like we have a magnet like that at the center of the Earth. But what we see, very similar, so at the center of the Earth, at the equator, notice how the line is flat to the surface, just like those iron filings were flat to the surface. As we go closer to the top, notice how they stick out more, they incline more. And at the very top, they would stick straight out. That is lined up with this magnetic field, like we're looking at here. Okay. We can visualize Earth's magnetic field on Earth without having to have, iron filings all around the Earth. We can use a compass to do this. You are familiar with a compass. And so we're familiar with one aspect of a compass, and that is, and I won't show you a compass because I know we're all familiar with them. And I'm just going to, so if I sketch something, the compass has a compass needle, and that compass needle will always point north because it is aligning itself within Earth's magnetic field here. It is pointing toward magnetic north. Now you have to turn your compass, to associate with that, but you can figure out, you're like, oh, that's pointing north. Here, I'll align my compass where north is north, or figure out which direction I need to go in. If you have your compass in your hand, and you've got, let's say you put north at the top, but your compass needle is actually pointing off to the side, then is north actually at the top? No, because your compass needle's not pointing that way, right? So what you're seeing there is you're seeing a difference in this. You're seeing a difference of how you need to turn your compass to accommodate what that north is. Now, another way to look at this is, let's say you align your compass needle here and you are on a hike, you're doing some orienteering in the woods, you're on a hike and you need to go directly east on your hike. So I know I need to go east on my hike. I get the compass needle out. I can't follow the compass needle because the compass needle is pointing north, right? So I have some sort of degrees. This is, in this case, 90 degrees east of north that I need to go to follow the path I need. The reason why I'm kind of saying this is because we divide that compass into 360 degrees. It's a circle, it's 360 degrees. We talk about that as magnetic declination. This is magnetic declination. So when you use a compass, you are used to magnetic declination, which is kind of how far am I off from north? What is the difference between this and north? In 360 degrees, we're around, right? So what is the difference in this? Declination. That is declination. Traditional compass, declination. Now there's another term, however, and that is a term called magnetic inclination. And so we see that here on this slide, magnetic inclination. Now, magnetic inclination relates to what we saw with those iron filings and how they were aligned in Earth's magnetic field. Now, you can't do this with a traditional compass, not exactly. So what you have to do is you have to have a compass needle that doesn't just spin around in a circle flat, but can move up and down with respect to the surface of the Earth. And that's what we see represented here. So you can see this little instrument here, where this is like our compass needle now. So notice that compass needle at the equator would lie flat. As we go closer to the North Pole, do you see how it points directly in to the magnetic North Pole, guess what it would do at the magnetic South Pole? Point directly out. And so the angle that we're seeing that is off of the horizontal, that is magnetic inclination. And I'm not going to ask you to measure inclination or declination, okay? It's just kind of basic understanding of what's going on with declination versus inclination. Now, this is, again, this is beyond Wegener's time. Why do we have to understand this? Okay. The reason why we understand this is because scientists began to study, so not just Earth's magnetic field, learning more about Earth's magnetic field, like we've just talked a little bit about, but scientists began to study paleomagnetism, past magnetism. Now, how do you study past magnetism of the Earth? Well, that is looking at this. Here we've got, you can see some lava that's come out at the surface. And that lava, certain types of lava, like for instance, remember basalt, so the lava that becomes basalt has a lot of iron in it. And so certain rocks that have a lot of iron in them can preserve Earth's magnetism, just like those iron filings were showing us the magnetism of that dipole. So they were showing us the direction of that magnetism. So when this rock forms, so in its liquid form, this is like the iron filings being able to freely move. Now, it's not exactly that, but it is like the iron filings being able to freely move because this is liquid. Once that rock solidifies and becomes solid rock, notice they're showing our temperatures coming down. Once that rock solidifies, it locks those in place. So this would be like, we take our compass needle, right? So I take my compass and the compass needle is pointing in this direction and I glue it down. It is not moving anymore. Okay. So we have now preserved the representation, the measurement of Earth's magnetic field as it was at that time. Now, what say I take this compass that I just glued down and I rotate it this way in my hand, right? So I'm going to rotate that compass that I just glued. Oh, this is a terrible sphere. Terrible circle, sorry. And now the needle of my compass is pointing in this direction. All right. And this is saying, well, this is north. Is this north? Is this direction north? No, I just had the compass here in image 1. I just had the compass and the compass needle was pointing north and that was great. And then I glued down the compass needle and then I rotated the compass off to the left. I rotated it counterclockwise and now north is pointing off to the left-hand side, but that doesn't mean that north is over there, does it? No. Now, if north isn't over there, that means that north didn't move, right? North is still in the same place. North is still north. Magnetic north is still north. So what moved? The compass moved, right? I mean, this is pretty straightforward. We're like, oh yeah, so you rotated the compass. Well, duh, you glued it down and then you rotated the compass. Okay. Why do I say this to you? When scientists started measuring paleomagnetism, okay, so you're looking at a rock, you're out there, you're looking at inclination, you're looking at declination, you're measuring paleomagnetism, and you start to see some interesting things. So notice here, if we are going through this example and we're just looking at different times of rock within the layers, and these are just times. So this is no million years, right? So this is 600 million years, 500 million years ago, 4, 3, 2, 1. Just as our example. And it's showing us our declination and our inclination here as measured in paleomagnetism. what scientists started to see was they're like, okay, 600 million years ago, they're looking at this and they're like, oh, north was over here. North was in this direction. That means the North Pole must have been close to the equator. Now, hang with me. Don't go with this. Don't leave like, yeah, 600 million years ago, the pole. Don't go with that. And then they went to 500 million years ago and they're like, oh, well, then the North Pole was here and then it was here and then it was here and then wait. Hang on. Did the North Pole move that much? Did the magnetic North Pole move that much? And the answer is no. And there was actually more to this because on different continents, they would see that different continents showed the North Pole in a different location. Like, say, this one's the one for North America. We've got rocks on North America. And then we went to rocks on Europe, and Europe showed that 600 million years ago, the North Pole was over here with paleomagnetism. And Africa showed that the North Pole was down here 600 million years ago with paleomagnetism. And so there was all this confusing data, like, why, wait, there were multiple North Poles and they moved and then, but guess what all of them did through time as we went to zero? They all joined up where it is now. Did the North Pole move over that time? Did the magnetic North Pole move over that time? Now, remember what we're getting ready to support. We're talking about plate tectonics here. This is a piece that leads us kind of back to Wegener. In other words, like with the compass just a minute ago, did the North Pole move? The North Pole didn't move. The compass moved, right? So the North Pole doesn't move here. What's actually moving? It's the continents that are moving, right? The continents are moving. And so with paleomagnetism, we see that the continents were, quote unquote, drifting. The continents through time moved. The magnetic North Pole stays at about the same place. It wobbles a little, but it stays at about the same place. But all the continents are moving, and we can see that movement through paleomagnetism. So here, when scientists start studying paleomagnetism, which is after Wegener dies, they have to go back and go, wait, wasn't there that guy who talked about continental drift? Now we've got more evidence that the continents are moving. Now, we still don't know how they're moving, which was the big thing that tripped him up, right? We still don't know how they're moving, but now we know that they are moving. Okay.